Картинки 3-4.
Что не
А потом
отвечает?
провертекс.
Ну, вроде нормально.
Вот только уберите
То есть,
дополнительно.
ничего, да, просто еще не может подумать.
Я всегда пробовал, понимаешь, проекте. В смысле, я просто из-за того, что я в голове живу, это ДП,
Видите?
я как бы чит,
Там пишет координаты атомов.
Вот тут уже.
Тут вот человек произведение, это хороший аргумент, но умелый, так сказать, использовать. То есть, для начала давайте так. Вот эта формула, все, она записывается, ничего не делает. Ну, там где только S, другой напишу. Но вот эти, давайте с них начнем. Чтобы было очевидно, что эти вот три вектора.
Так, звук вроде включил.
Да.
Окей.
Очень хорошо. Я думаю, но вот чтобы во всем было три.
Ну, тут надо немножко как бы усилие будет здесь, потому что понятно, что там успею у
Окей.
тоже
Спасибо.
Я знаю.
Я как бы
здесь.
А это надо?
Здесь все уже будет. После усреднения вот эта штука.
Что я знаю.
Я справлю. Что он справляет, видимо. А это
Я превзошел задачу. Видите, вы сами можете текст быстро и правильно сказать. Надо еще думать, короче.
Источник жидкости не в этих произведениях, а синус линии, например, произведение, потому что произведение, оно не численность не влияет.
Ну, как текст, да.
Да.
Ну, как-то надо делать явно.
Right? Shall we start? Today we have a pleasure of listening to a talk from Junhui Cao, the member of Picoseconds Center, a very industrious one, and it is reflected in the fact that it is his second seminar this year. The first one was about superconductivity, and now about XY simulators, Polariton XY simulators Revisited.
Thank you, Anton, for the introduction. Appreciate everyone to join this seminar. So my topic today is about our recent work on the Polariton XY simulators. So special thanks to our doctor student Denise and our supervisor Alexei. So let's get started. So, in the topic, I will mainly first introduce the background for this research, and then I will introduce the theory that we developed to overcome some problems in the XY simulator. And for the third and the fourth part, I will introduce one-dimensional chain lattice and the two-dimensional triangular lattice as a numerical example to show how the XY simulator works. And then I will make an outlook for the topology in the Polariton lattice. So this is not included in our work, but recently I made some effort on this part. I can show you that this topology XY simulator or our theoretical work has a very large playground. And then I will give a brief conclusion. So first, I will introduce the background. So actually, the motivation for this work is based on the work which was done by Professor Berloff and Professor Lagodakis in 2017. So in this pioneering work, they realized the classical XY Hamiltonian in the Polariton simulator for the first time. So for example, here's a model that they consider, and this is the experiment implement, and this is theoretical simulation to this experiment. Here you can see that the direction of these arrows should actually can be mapped to the spin or pseudo spin of the polariton on each side. Here's the antiferromagnetic coupling, and here's the ferromagnetic coupling. But yeah, so because this is a triangle lattice, so usually there will be some frustration due to the especially the geometric frustration. And you can see that this coupling is ferromagnetic, but this coupling is antiferromagnetic. But in this paper, still there's something need to discuss. First is that the Hamiltonian that brought in this paper is phenomenological, and then is that the claim that the state that carries the highest number of the that will minimize the XY Hamiltonian. So this is still in debate. And I will show you how in our work that actually this mode can be selected by the different compound.
So this Hamiltonian, was it the actual Hamiltonian of the evolution of the system?
Use the Gauss-Pilaevsky equation to
Just add, sorry.
okay.
Please your microphones if you don't want to say anything.
Microphone's muted.
Okay.
Sorry, highest number is what?
Sorry, the high state that carries the highest number will minimize, so there's no off. Just a misprint. Okay. Actually, in this work, they use a Gauss-Pilaevsky equation to do the calculation, and then will result arrive this result, this phenomenological Hamiltonian.
So this was actually the Hamiltonian to which the dynamics of system could be formally mapped.
XY simulator, yes. This is actually the XY simulator Hamiltonian. Okay.
In the second statement, the highest number of what?
Sorry, there should be no off. Okay. Here's the highest number.
It was the highest number of what?
Of particles. Yeah. Particles. So N here, the particles will minimize the XY Hamiltonian, and this means that the state will choose the system will choose the state that with the highest number of particles. I will show you later. So here comes to our work. So first is that maybe I need to introduce something about the Polariton, as maybe not everyone knows Polariton, how Polariton works. So this is just a very simple Jennings-Carnes model, where you can have this EC, it's a photonic mode, and EX, it's the excitonic mode. And this coupling is done by the Rabi splitting. And then the eigenstate of this Hamiltonian will automatically give you the Polariton condensate. So in experiment, actually the Polariton condensate can be formulated by the pumping. So here, for example, at each lattice site, and there will be a pump, and then the Polariton condensate will be pumped here. But actually, firstly, if you consider a non-resonant case, that is, the pump will generate this exciton reservoir, and then this exciton will decay all through the coupling, and will transfer to Polariton condensate. So the first point in our work is that we use a Hankel function as a solution for the Polariton wave function. So why to use a Hankel function? That is, if you observe the tails that observed in if you look at the tails that observed in this beautiful experiment, and you will see that this is actually the signature of the interference between the Hankel wave function. And another thing is that if you use a very small pump, for example, a delta function, you can treat it as a delta function. Then this is a source point diffusion PDE, and but this is in 2D, and automatically the result is a Hankel function. Then one can define the overlap matrix element. So this is just the overlap integral of the of two sides. Here maybe we can only consider the nearest neighbor, means that j equals to I plus 1. So this is for nearest neighbor.
So Hankel function of the second kind and of the first
Yeah,
kind?
so this is just the complex conjugate, yeah, for the H1. So
What is KC?
yeah, this Kc is actually the in-plane wave vector of the Polariton constant. So or we can write it as Kca. It's real. Kc can be real. It's a good question actually. Kc can also be complex. And this will express the decay of the Polariton constant in the real space. But if it is complex, and then the imaginary part can actually be put out, and you will find it is exponential decay. Now here,
What's the difference between nominator and denominator?
yeah. This is J and this is I. So I means that
Just normalization.
yeah. Just normalization. So if J equals to I, then this is this is 1. So this is a diagonal term. So if J is not equal to I, then this is coupling. Here we only consider the nearest neighbor, and then you will have your overlap matrix, which is D. So the size of D, it depends on your the number of the sides. For example, if you have n in total, you have n sides, then the size of D is n by n. And do the diagonalization to this overlap matrix, you will automatically find the eigenstate and also eigenvalue. So here is some numerical.
They can stay so what? Of overlap matrix.
Yeah, of the overlap matrix.
So it's not. This is not some physical operator. It's just you want to diagonalize this interference pattern.
Yeah, and I will show you that actually this is equivalent to the tight bundle Hamiltonian, and also equivalent to the XY Hamiltonian. And this is some numerical result that for the delta pump and where you have a finite width Gaussian pump, you can see that if the spacing between the site is 10 micrometer and the size of pump is smaller, far smaller than the lattice spacing, and the Hankel function is actually a very good answer for the wave function of the Polariton. Okay. Then I will introduce the mode selection mechanism. So this is remember that in the paper of Berloff, they argue that the mode with the largest number of the particle will dominate this system. But here actually it is different. It is related to the eigenvalue of the overlap matrix. So here we can show that the mode actually with the smallest eigenvalue will have the highest growth rate when the pump power is low. But if you increase the pump power, you will find that the mode actually with the highest eigenvalue will have higher growth rate when the pump power is large.
How do you define these growth rates?
Growth rate is by dn over dt. N here is the number of the Polariton constant.
So you run the simulation across Pelaevsky to D.
Here no gross Pelaevsky equation is considered. So this is from the red equation. Okay, we can
So we use the same method for the number of particles and power.
Yes. Actually, the number of particles is proportional to the eigenvalue of the overlap matrix that we defined in the previous slide. But here you will see that the different eigenmodes can be selected on the different pump powers due to this growth rate. If the mode with the highest growth rate under some certain pump, then this will dominate this system automatically. Right?
But could you actually show the equations you were solving?
IBS.
Equations.
Sorry, what should I write here? IBS, IBS?
Please switch off your microphones.
Okay. This is for this Pukyong National University.
Pukyong National University. I see. Yes,
Okay, thank you. I didn't put the equation here, but this is a result of the paper. We can discuss this later.
Why small powers is dn by dt negative?
That is because of the decay rate. So you always have a decay which is proportional to your particle number, right? So this is why the mode with the smallest eigenvalue with the intersection of the y-axis is the largest. For the largest eigenvalue is the smallest. So the advantage of this theory is that we can simply map it to the XY mode. So first, it is our overlap matrix, and this beta is actually equals to the overlap matrix element. And first, you can see that it is equivalent to the tight binding Hamiltonian. So tight binding Hamiltonian, this I and J is actually the nearest neighbor coupling, which is also defined in our overlap matrix. And use a Hostan-Primakov transformation after some math, and you will find that this.
Wait, hold on. So in the tight binding Hamiltonian, for the Hoping matrix elements, you don't have literal overlaps of wave functions. You actually have the matrix elements
of Hamiltonian,
of the perturbation
kinetic energy and the potential. I know what your concept, but here actually you can consider that the kinetic energy it is uniform, right? But so they're just integrals if the lattice or the proportional to the integral, but the potential. It is also there. Here's no external potential or anything is considered in this system for the.
So if they calculate Hoping elements, these Hoping elements just as it is.
Overlap of two wave functions.
Yes.
Is it dimensionally correct? Even
Dimensionally, no.
You need some energy.
There's some energy here. Well, I think they have some energy.
Yeah. So for tight binding, actually there's a Hamiltonian inside it. That means that you have the kinetic energy operator and also the potential. But the kinetic operator it is translational invariance, right? So this means that if the external potential is zero, and strictly speaking, that this is equivalent to the overlap matrix. So
You couldn't just multiply Hoping by energy
of the kinetic energy. Yeah.
At the side.
Yeah.
And this will be Hoping.
Yeah. Yes.
Energy.
Yes. So yes. So
Okay. So this model only accounts for kinetic energy. So literal Josephson tunnel.
yeah, literally Josephson change it.
But no
But no dissipative, no dissipative, and also no external potential. But maybe actually you can also consider it since the system it is symmetric, and the overlap matrix is actually find that a matrix element it is equivalent for the tree diagonal, right? So okay. So after some map, and you will find that this tight binding Hamiltonian, so it's actually equivalent or we can say it's isomorphic to the XY simulator, to the classical XY Hamiltonian. One thing I need to mention is that here we did not consider SZ term. So, but SZ term is actually important if you consider this is this is no longer a classical XY Hamiltonian, but quantum XY Hamiltonian. This actually works as some fluctuation. But since we only consider this two-dimensional case, and SY SZ can be naturally eliminated, and this will be a classical Hamiltonian. If you consider SZ, then there will be more interesting physics like PKT phase transition, and also some other many or the XZ model. Okay. Here, so actually the sign of the J or sign of J, which is the element of the overlap matrix, will corresponding to different one states. So if the sign of the coupling constant, which is negative, and you will anticipate that the ground state of this Hamiltonian is a ferromagnetic state. But it is if it is positive, it means that the ground state will be antiferromagnetic.
Can I once again criticize? So we started with something that looked like a mean field approximation and classical physics. That now we switched to operators, and it appears that it is quantum. So kind of second quantization.
Yes. So if you consider, as I said, if you include the SZ term here, then this is a quantum XY. But if no, because the commutative relation between SZ and SX and SY, it will give you something like a IH bar.
No, but you should derive commutation relation for you CI, CJ operators. How do you define them?
This is classical. Yeah, this is classical. This is purely classical because.
And then you just make mapping between C, G, and
J and D.
Yeah. And spin.
Yes.
And then you say now it's quantum.
No. I didn't say it's quantum. It's classical Polariton XY simulator. If you consider SZ, then this will become quantum. But if you do not consider SZ, since we work on the two-dimensional plane, and then this is classical. Okay, so I will show you some numerical result for this theory. So first, so this Hamiltonian in the one dimension. So it's a chain lattice. The Hamiltonian will only consider the nearest neighbor coupling. Also, you can consider next nearest neighbor coupling, but there will be another story. Also, I will agree that there will be much more interesting physics if you consider the next neighboring coupling, but not down here. You find, for example, here beta equals to 0.1, and this is eigenenergy, and for this eigenenergy with different beta, or let's say the sign of beta, if you give you different ground state. For here beta, it is positive, and then you will anticipate antiferromagnetic coupling or the antiferromagnetic phase. So here is the real space when for the ground state where k equals to pi over a, and here is the phase of the Polariton concept. And
I would expect that all eigenvalues of this D are positive. Is that right?
D, you mean?
Matrix.
D matrix, not necessarily. It can be negative.
Can be negative.
Yeah, it can be negative. I will show you it to you later.
But once again, so these figures are from simulation, and you were solving the Gross-Pitaevsky.
No. From the diagonalization of this overlap matrix. in our work, there's no Gross-Pilaevsky equation. So
Discrete model, not continuous model.
uh-huh.
It's like a discrete model, type binding model.
Yeah. Type binding model. Yes,
And
exactly.
then you plotted the wave function as the superposition obtained from the coefficients.
Yeah, from the eigenvalues, yeah, or the diagonalization, yes. And this phase, if you look at the phase at each different site, it is just the opposite, and you can map the sign of the phase to this beautiful pseudo-spin structure. So you see the up down up down up down. This is antiferromagnetic. And also I also compare some other eigenstate for for the state with the highest eigenvalue, so this is purely ferromagnetic. This is
blue and what is yellow?
you where
Left column, yeah, this blue.
so this blue this is the intensity of the wave function. Yeah, blue means that there.
Absolute value of that space.
Yeah, here is the phase. Here is the intensity.
And what is actually changing the K vector?
Yeah, the K vector. So this correspond to different eigenstates of the Hamiltonian. So K vector is exactly the same as a block pseudo wave vector here because it's in the lattice. Yeah. Since it's much more clear in the triangular lattice, so first you see the Hamiltonian is still the same, but we also only consider the nearest neighbor coupling in our system. So this is a triangular lattice. This is in the reciprocal space, and if you look at the structure of the Hamiltonian or say of the overlap matrix, you will find that this is a tri-diagonal overlap matrix. This is exactly the same with the tight binding model, but if you look at the fine structure of this overlap matrix, and you will find that here this is tri-diagonal term. So this is the intercell coupling. Here we will describe some. So sorry. So this is inner cell. This will correspond to some intercell coupling. And
wait, you have single site per unit cell.
Yes.
And you should have only three, and you take into account only nearest neighbor quadrant. So in the matrix should be only three. At each line you have only three non-zero elements.
No. For example, here you have 6 here. Here you will exactly have 6 components.
But why then they just
because there's edge. Yeah.
Such a structure.
Yeah. So if you consider a pure perfect periodic structure, then this will not give you any edge state. But if you consider open condition, then there will be edge state. So then I will show you how the beta, which is overlap matrix element, will change when we tune the different Kc. So Kc here is in-plane wave vector for this Polariton condensate. And you will see that actually the real part of beta, which is the hopping element, or hopping intensity, it is oscillation with the change of the Kc. So this actually answers the question why is beta positive or negative. So actually it depends on Kc. And you find that if beta is positive, and the eigenvalue of this Hamiltonian for the triangular lattice, so which is 1 plus 6 beta, and another eigenvalue is 1 minus 3. So if beta is positive, this means this E plus will have the highest energy, and this E minus will have the lowest energy. So, but if beta is negative, this is just opposite, And this means that this E minus will have the highest energy, but the E plus will have the lowest energy. So actually, this is something about the ground state. So for for the real for the positive beta, the ground state is actually as a gamma point. But for the negative beta, and then the ground state will be at the K point, as I will show you to you later. So still we can place this figure here. So for example, we choose Kc equal to 1.95 and also 2.9. So when
What's this Kc?
Kc is the in-plane wave
I
vector.
understand, but how does it rise in what is the value in the experiment?
So the value in experiment is typical. This is a typical value, 2 micrometer.
Depend on some parameter.
This is actually depend on the blue shift of the Polariton condensate. So if the blue shift is high, it means that the exciton will tend to repel the Polariton, and then will gain a very large in-plane momentum. But if the blue shift is small, then the exciton will have length effect on the propagation along in-plane propagation or in-plane diffusion. And okay, so here's some numerical result. This is the band structure, and you will see that exactly when Kc equal to 2.9 and the beta is negative. So here is a gamma point, you will have a ground state, but in the K point, you will have the highest energy. And this is just the opposite when beta becomes positive. And here in the gamma state, gamma point, you will have a highest energy, but in K point, you will have the ground state. But for K point, this is actually the antiferromagnetic phase. As for the gamma point, this will map to the ferromagnetic phase. So here you can see that this is a phase parting of the system in the antiferromagnetic phase. So because there's geometric frustration, and you will see that actually the spin between two neighboring sites is actually 120 degrees.
Junhui, a naive question. I would think that regardless of the sign of beta or the Hopper matrix elements, you will anyway have two bands with in the spectrum, two bands crossing at Dirac codes. It's basic properties of graphene.
But you have two tablets when in graphene. That's why you have conical version.
It's a trigonal lattice. Sorry, my mistake.
Okay, no problem.
But I have also a question. Then I don't understand why it's possible to consider nearest neighbor coupling if you have a matrix element between Hamiltonian function, because usually in solid state you have highly localized states which overlap exponentially, but Hamiltonian function overlap.
Zero. Yeah.
Two overlap exponentially if Kx and Kc is
Complex, yes.
But here it is not.
In this case, it is not.
This is a good question. So actually, Hankel function is not a localized state, as you mentioned, yes. But here, if you compare the only the nearest neighbor coupling and the next nearest neighbor coupling inside this box, because Hankel is not only not localized, but the normalization is divergent. So the norm of Hankel function in the whole space is divergent. So this means that you need to use some box normalization condition to fix the integral of the Hankel function inside this whole system to be one. Yeah, and then you can compare the overlap matrix between the nearest neighbor and the next nearest neighbor, you will find that the ratio between them is actually very large. It's about 10 to 1. The ratio between the nearest neighbor and next nearest neighbor is about 10 to 1. So here you can make this simple assumption that we can only consider the nearest neighbor coupling here. But as I said, that if you consider next,
This ratio is so small.
Is it because they're oscillating?
yeah, oscillating, but there's also some decay feature.
Overlap is not oscillating because
Decay feature.
if you multiply Hamilton of second type to Hamilton of the first type.
But they're from different points.
Yeah, but different, yeah, there's some decay feature for the Hankel function. Yeah, thank you for your question. That's, yeah. Here's some time scale when you consider the pump, but this part is actually calculated by Gross-Pilaevsky equation. And you will see that the whole system will reach its quasi-equilibrium state at about 15 picosecond. So this means that the XY simulator is actually possible very fast, ultra fast, which can be where the eigenstate or can be reached within 100 picosecond. So okay, so I also made some calculation for random lattice. Here's the 5 by 5, but add some dispersion to the position. So some important feature can still be obtained. For example, the antiferromagnetic phase and the ferromagnetic phase. This suggests some robustness for the XY simulator against the weak disorders. So it means that in the experiment that you can anticipate even some very small disorder will not make your system invalid. Okay, so here's some new results beyond this paper. I really have a discussion with Artem. So on the topology of the Polariton lattice. So I think this is very interesting playground for the for our theoretical model. Strictly speaking, it's the overlap matrix. So yeah. Still for the, let's start from the simplest one. So it's a one-dimensional SSH model. There's some inner cell coupling, which is T1, and some intercell coupling, which is T2. And the T1, T2 actually can be related to your lattice constant. Here also, if you consider the overlap matrix, because the distance is different, and this will give you different matrix element, right? So yeah. So here, if T, so this is just a very simple result from the SSH model. So if T2 is larger than T1, and then the winding number is 1, and you will anticipate two edge states, like this. And but if T2 is smaller than T1, then this is trivial. Trivial can, you will do not have edge state or the winding number. But the most interesting thing that is that you can consider two SH ladder or double SSH, for example, here. So this can be actually manipulated in the Polariton lattice very easily. So you can just tune the distance or tune the KC, and this will give you different coupling constant or hooping constant between the sites, and this will provide you a playground to study the physics of the double SSH or the cruise ladder.
Sorry, I'm not familiar. Could you explain it? This model, is it non-reciprocal coupling? It appears that the coupling's matrix elements in two directions are.
It can be non-Hermitian coupling. It also can be some real coupling. Yeah. So if you consider in the two-dimension case, then the topology will be very rich. Topology physics will be very rich. For example, here I show you some example of the Kagome lattice. So especially breathing Kagome lattice. For the conventional Kagome lattice, so T1 equal to T2 and A1 equal to A2. So A1 is yellow and the A2 is blue. And in this case, this is a perfect Kagome lattice, and you can write on the expression or the Hamiltonian and calculate the eigenvalue. This is a flat band, typical flat band of the Kagome lattice, and this is some dispersive band. Here's the result for this Hamiltonian, and the most interesting is that you consider breathing Kagome lattice, and in this case, the parity symmetry of the lattice is broken because T1 does not equal to T2. However, the time reversal symmetry.
Can I ask something?
Yeah. Thank you.
Can you go back one slide?
Sure.
With with Hamiltonian, just one other. Yeah, you have 1 plus exponent. Yes, but you can also write to the neighbor.
Yes.
But you can also write positive exponent and negative exponent back and forth. It will only change the phase factor in front of each term. But for energy spectrum, it will give you exactly the same answer because it's Hermitian, Hamiltonian, same eigenvalues. But for other things, it's actually like if you try to calculate transitions between states or other things, this phase factor is important.
Yes.
I look at this Hamiltonian and I can see that it has the symmetry of the lattice. But
Yes.
it doesn't necessarily, it will give you a different answer. What defines the choice? Why do you need to have it with the symmetry, with the translational symmetry of the lattice, rather than with how Bloch or people who introduced it? It's just the Fourier. Fourier, you need to put all coordinates. So you need to go back and forth, and that gives you more insight if the distances are slightly different between neighbors, and it gives you real geometry. So why do you use this one rather than the canonical? Because this one also makes K and R not conjugate momentum and coordinate not conjugate quantity.
I see. Thank you
You
for the
understand?
comment.
So I'm just asking why would you put 1 plus? It probably is more convenient for diagonalization, but or you never calculate optical transition, or what is the reason to choose this phase?
So actually, this is as you mentioned, this is a simple result after you take the Fourier transform for the system. As you see here, you have actually you have a remember that we in the hexagonal lattice we have only 2 sublattices, but here we have 3 sublattices.
Yes.
Yeah, and this is just analog to the hexagonal lattice.
It does not matter. I agree. I agree that it could become. But if you, my question is actually, I probably did not distill it. My question is, for the results, do you only need to for energy spectrum? Then it doesn't matter. Or are you going to use something else, your eigenvectors, to calculate anything else in addition to energy spectrum?
Here, I think the energy spectrum is it is okay. Yeah, just
it is okay. I have no doubt. It doesn't matter. Energy spectrum is perfectly fine, but you are not going to do anything beyond the energy spectrum for that.
No, anything beyond the energy spectrum, because
that's it. Thank you. I will not hold you more. Okay, thank you very much.
Thank you for the comment. Because here we only consider the band topology, so only the energy band is important. Thank you for the comment. Yeah. Okay. So let's get back to the breathing Kagome lattice. So the result of the broken parity symmetry will give you some non-trivial chain number for the band. However, okay, let's see. We have 3 band here, right? But because time reversal symmetry is not broken, it means that the total chain number is 0. But if the parity symmetry is broken, for different band, you can have a different chain number. But also the total chain number can be 0. But for subband, it can be non-zero. Okay. So here's the result that for example, this is
why do you have one band dispersionless? So
flat band. Yeah.
why does it derive?
This is derived just from here, the perfect Kagome lattice.
I understand, but what does this property of symmetry?
Yeah, this is a property of symmetry.
By what?
C6 symmetry. Yeah. So if A1 equals to A2, this is the C6 symmetry. And but because of this is so for C6 symmetry, there's here you have the three sublattices, and the interference between the A1, A2, A3. So actually you have 3 vectors, but in fact only 2. You just need 2 bases to describe your system. Then there will be 1 extra, and this can be interference deconstructed. Yeah. Yeah.
And this is that's why.
Yeah, this will give you a flat. Yeah, exactly. And okay. So for this breathing Kagome, you will find that the gap is actually open. Because of the parity symmetry is also broken, and the most interesting part is about the edge state, because parity symmetry is broken, and we can anticipate some edge state here. For example, this is the eigenvalue of the Hamiltonian. So this is 0 energy here. The 0 energy in the breathing Kagome actually correspond to the corner state, which is highlighted here and here. And if you further increase the energy, then you will re-enter the box state like here. Okay. So another very interesting aspect for this is that if you consider the breathing Kagome lattice T1 is not equal to T2, but if it is complex, they will become like a Hodel mode. And because this is the hopping is complex, then the time reversal symmetry is broken. And then the total chain number for this for the 3 band will be non-zero. For example, but also you will find the very interesting thing is that the flat band is no longer flat, but because of the non-Hermitian physics, and so here T1 for numerical calculation, I use a T1 to exponential 2i over 3 pi. It means that in the if you consider a loop over this very small triangular, and the phase is gained by 2 pi, and yeah. So for this case, if you tune the intensity between the T1 and the T2, and you will find the chain number can be tuned from the 0 or -1, -2. So for -2, this is the typical higher order topology insulator for the breathing Kagome lattice. And also you can change the phase just to I. So this means that in the loop you gain the phase by pi, and the chain number, the total chain number is 1. Okay, over.
I have a question. So this classification according to your numbers is
Wilson loop
is good, but the problem is here you have bosons or fermions, because for fermions why it is at least theoretically important, because this classification usually is used for bent insulators, for example.
Yes.
And then, based on boundary correspondence, you can speculate about appearance of H states in the gap. When Fermi level is in the gap, in the null.
Yes.
But here, if you apply this to for bosons, your ground state, what is the ground state? They all condensate at the minimal energy. Is it the case? So they don't feel whole band.
You mean the occupation?
Yes, occupation. And why then it is important to calculate Chern indices or any indices in this model?
It's a good question. So you can not only consider boson here, but you can consider the hard boson, hardcore boson, right? They have
Which boson?
hardcore.
Hardcore.
Yeah.
Hardcore.
Hardcore boson. So they can work as Fermi. It means that the repulsion interaction between the boson is very strong, and that they cannot easily form a condensate, right?
Okay.
Also, so this is not only for the electrons, but for some photonic crystals and some acoustic phonon crystals. They use a similar structure to formulate the topological insulator. Okay, so this is what I represent. So I think the note for our system is that we provide a fully analytical model which links the overlap matrix of the Polariton condensate to the effective tight bonding Hamiltonian and also the effective XY simulator. And we also brought us the mode selection mechanism. That is, you can select the mode as you want by tuning the pump power. And we also show the robustness of the experiment implement by consider the some slight disorder away from the fully perfect triangular lattice. And I think there's still some very promising playground for the for this Polariton XY simulator. For example, as I show you that it can be this pattern can be automatically formed within 100 picosecond. This is very fast. And another thing is that if you consider a quantum case, that is, you consider the SZ term. Maybe you can by adding some external magnetic field to different sites, and you can formulate the SZ at different sites, right? And this might give you some more interesting physics like a Piketty phase transition. And also, if you consider the next nearest neighbor coupling, and then the physics will be more rich, much more rich than this way. And okay, at last I also show you the potential for the XY simulator or Polariton lattice for the Polariton topological insulator. Okay, that's all. Thank you very much for the seminar. Welcome for any question.
Okay, so do we have questions in Zoom? If not, then
Does your
yeah, I do have.
overlap matrix have exactly zero eigenvalues?
Overlap matrix?
D is D matrix. Does it have exactly zero eigenvalues?
Yeah. So if you consider the edge state, the edge state, then there will be the zero energy, so which corresponds to the edge state.
I mean, you can consider the set of eigenvalues of this matrix as some measure of linear dependence between these Hamiltonian functions on the different sides. Yes. So, of course, they overlap. That means the number of linearly independent states of them is actually less than the total number of sides. And so there must appear exactly zero eigenvalues, which means that the rank of the D matrix is less than its dimension.
Yes, exactly. So I can show you it.
And this corresponds physically to these H states, right?
Yeah, to the edge state, but also in some trivial case, maybe you can find we show you yeah, here you can see that the
screen, please. Share the screen. Here's the
I have shared. I have shared.
Sorry.
So okay, you find that the real part of the Hopi matrix, which is the element, it can reach zero at some certain cases. So exactly this case means that there are some construction overlap and some deconstruction overlap, and the total effect is there.
This means that the number of these linearly independent elements of the set of the Hankel function sitting on different sides is less than
less than dimension, yes.
And one technical question: how do you calculate this overlap of Hankel functions on different sides?
So good question. So this is actually a numerical achievement. So that's because Hankel function, the integral of the Hankel function or the norm of the Hankel function in the whole space, it is divergent. It means that but our system is finite. That means that we can do a normalization inside our system. So this
but how do you calculate technically? Just you have two functions sitting on different sides, and each of them is actually symmetric above the side.
Yes.
And then you have this box which breaks any symmetry. So do you calculate numerically?
Numerically,
point by point, like two-dimensional integration.
Yeah. So
there is no some re-expansion of
noise. That's too complicated, and yeah.
But in principle, it is possible to normalize on delta function, so on K.
Yes, exactly. Yes, in principle, it can be done.
And avoid considering of large but finite volume. If you normalize each Hankel function to delta function, I can show you.
Okay, thank you. Okay, thank you. Thank you for your suggestion.
Not whose Kronecker symbol, for example, when you normalize plane wave in box.
Yeah, this actually is equivalent and not equivalent, analog to the normalize of the plane wave in the box. Yes. Until
we have also a question on Zoom. Right. So there was a question and raised in Zoom.
Yeah, hello. Can you hear me?
Yes.
Yeah, so thank you for your talk. I had a question on the mode selection mechanism, which you showed on the slopes of dn over dt. Yes, this one. So as I understand, you derived the way how, based on the pump power, you can say which mode number will grow faster. It is clear to me. But on the next slides, you mostly show how different phase patterns, how different modes exist based on the planar K vector. Can you tell how do you translate from the n mode, for example, 10th mode or something in the system, to the number of K vector? How this correlation?
Okay. Good. Thank you for your question. So actually, if you have n sites, then in your overlap matrix, then you have n by n. The size of overlap matrix, it is n by n, and you diagonalize this matrix, it will give you n eigenvector, right? This n eigenvector in the if you consider the block pseudo wave vector, it will also give you n pseudo vector. So maybe I can show you here. Yeah, it will give you n pseudo wave vector, and this n pseudo wave vector will correspond to the for example, the first Brillouin zone, and you can cut it from the k equals to minus pi over a to pi over a by n blocks. So this will give you n k values in this case.
Okay, so it means that, for example, if we are very close to threshold and the first mode wins, it will always be the mode which corresponds to the first block to the minus p over a. Am I right?
Depend on the eigenvalue. It depends on the eigenvalue. So So if you as I showed that the dispersion for the Hamiltonian or for the overlap matrix looks like this. Depend on the choice of the beta, and you can have you can have different eigenstates, and this different eigenstate, for example, here when k equals to pi over a, you have the ground state, which is where the energy is a minimum, and for some other k, for example, k equal to 0, this is highest energy, and this in the mode selection, in the mode selection, actually this eigenvalue will correspond to this different k, because this is in the lattice, right? Pseudo wave vector. So for example, here n1 equal for this one-dimensional system, it will correspond to the AFM phase, where k equals to pi over a. For this nn, this will correspond to k equal to 0. So where you have the ferromagnetic phase. Thank you for your question.
Okay, thank you.
May I also ask, so since we're on this slide, by construction, the model is Hermitian in your case. There are all parameters are real, right? Did I understand correctly?
Not exactly, because the overlap of the Hankel function will not give you a purely real number.
For the matrix elements, so complexity is allowed, but for the eigenvalues.
For the eigenvalues, yes, this is real.
Okay, so the model is Hermitian. And how do you then calculate the growth rates at this slide, please?
Okay, the growth rate is, you can couple the rate equation of the Polariton lattice and couple the rate equation of the epsilon reservoir. So and you can consider in the quasi-equilibrium state for the epsilon reservoir, for example, partial n partial t of the reservoir is almost approximately 0, and you can then you will have a relation between the pump power and the number of the Polariton mode, and you can substitute this equation to your Polariton rate equation, and then this will give you some dependence of the Polariton rate equation and the pump power. This is what we consider in this case.
Questions?
Okay. If no, thank you very much for your attendance.
So red button.
Okay.
Yes.